So as you said, I'm Tyler. This work was done with my advisor, Rob Garrett at Cornell. This is going to be, again, modeling, so not as many pretty pictures, but some plots. The work is going to be looking at the effects that a grain size distribution would cause to a model. I'm going to explain a lot. I have plenty of warm-up slides as well, so plenty of background to get through first. So let's just get on to that. The major background questions that this work is going to try and address is where and how could chemical complexity thrive? And again, coming from an astronomy department, we're not talking about things like rocks or atmospheres even, but molecular clouds. So these molecular clouds or interstellar clouds are the places where stars are forming, and eventually planets will form around those stars. So to look at those regions, you want to think about what environmental parameters you need to think about, densities, temperatures, UV field strengths. You need to look at chemical pathways. This is where the laboratory chemists come in. They need to tell us what reactions we should be thinking about, what barriers they have, what rate constants we need to put into our models for. I'm going to be looking at the building blocks for complex species. So this is kind of breaking it down to the very beginning. Like Brett showed in the warm-up talk, this will be looking at things closer to methane and water and methanol rather than methyl formate or anything more complex than that. And then the model parameters that I need to put into my model to make this thing work. So again, plenty of rate constants, plenty of barriers, and plenty of chemical species. So applying this model to a quiescent dark cloud, quiescent just means it's static. It's not yet collapsing. It's not entering the protostellar phase, so it's fairly boring, as you might want to say. But it is a large region of overdensity. The density here is around 10 to the 4 particles per cubic centimeter. I think most people could realize that's a fairly low number. It's a pretty good vacuum, but it's still more dense than your average interstellar space. An average dark cloud, interstellar cloud, has a total mass of 10,000 to 1 million solar masses. Solar mass, again, the mass of the sun, 10 to the 30 kilograms. So it's a lot of mass. And the places that I'm looking at have a temperature of around 10 Kelvin. So the low end of these spectra that have been shown in the terahertz. We're going to assume some elemental abundances for this model with respect to total hydrogen, showing that I have a C/O ratio of about 0.5. That can vary. It depends on what stars you're around or what stars are affecting the environment. But this is just what I've used. And the model will involve more elements, but these are the only ones that really matter. You can see that I list atomic hydrogen as 5 times 10 to the minus 3 with respect to total hydrogen, because most hydrogen in this dark cloud is locked up in molecular form. Okay, so I'm not sure how well this is going to translate. I think you can see it. There are these dark clouds here. This is just a picture of the night sky with a fairly good camera, and you can actually see these dark clouds imprinted on the background field stars. So these are very large regions, and you can't really tell that it's there apart from the fact that it obscures the stars behind it. The easiest way to observe what's in these clouds is to find a reference star near the edge of one of these clouds and take spectra of that star and notice how the star's spectra, maybe compare it to an average star that's not being obscured, and see how that cloud is affecting the spectra of the background star. So doing this, mostly in the submillimeter or the radio, looking at that one I just showed, which is the torus molecular cloud, it's kind of the archetypal molecular cloud. This is just showing you a list of the gas species greater than some arbitrary cutoff, just to show you that there is a diverse amount of gas species. There's plenty of aliphatics or other just carbon-bearing species. There's plenty of nitrogen-bearing species. There's some interesting oxygen-bearing species, and even one that contains sulfur, although I generally neglect sulfur because it doesn't do anything interesting in my models. And then here is just a large table that has more information than I needed, but it was a good reference. So this is for ice abundances, and this is generally done with infrared band absorption. And the interesting ones I've tried to highlight, you can see this is just listed as a percentage of water ice, and this ice is forming on dust grains. So this large cloud is mostly gas, but it does contain about 1/100th of its mass in dust, and this dust is usually either silicates or carbonaceous. And as this cloud just sits there, the gas species will collide with the grain surface. You assume some sticking parameter, and things just start accreting onto the dust surfaces. And as these things accrete, we call them ice. And you can see that the first 5 columns here are stars or protostars. Elias 16 is a background field star for the molecular cloud, whereas these 4 here are protostars. So that's past the point of quiescence. It's started to collapse and the center has started to heat up, and it started to thermally process the ice. And so CO is the most volatile ice species, so its composition is decreased. The composition of the ice as CO is decreasing. You can notice that the CO2 is relatively constant, which implies that it's a relatively robust mechanism must be forming CO2 in these regions. And then the rest that I've highlighted are just kind of interesting things that we'll be looking at later in my plots. One particular thing to note is methanol. In the least processed ices, there's not too much methanol. In the kind of intermediate processing stage, there's quite a bit of methanol. It's actually the second most abundant ice in some protostars. And then in the highly processed protostars, where the protostellar disk is starting to be evacuated by the heat of the inner star, methanol starts to decrease again. And this just points to high processing, either evacuating the ice off or sublimating the ice off of the dust surface, or even just decomposing some of the more complex species. The last column here, besides comets, Sag star, is the center of the galaxy, where there's just a large, very interesting molecular cloud that's being irradiated by many different sources. And so it's kind of an outlier and hard to model. So how am I going to model this? I use a rate kinetics model. It's essentially something that you've probably all done in, say, a high school chemistry course. You just have a couple rate equations for a chemical species to evolve or to react with some other chemical species to form another one. And then you have, instead of one of those, you have 12,000 reactions now. And they're all coupled with 1,200 separate chemical species reacting using 12 elements. You have to specify those local environmental parameters again. And you evolve what's initially an atomic gas, with the exception of molecular hydrogen generally, just through time, just letting the reaction network do its thing. So most reactions here are not going to have a barrier because there's enough reactions that if anything has a barrier, it's probably just going to be safely ignored. All gas phase reactions essentially are barrierless. The solid state reactions can have a barrier, and that gets a little more complex. It is a three-phase model, so we worry about gas species, we worry about the accretion of the gas species onto a grain surface. You have grain surface reactions, and then you have an ice mantle where more reactions can occur, but you can also just sequester species. You can kind of imagine how this model works. It is not spatial whatsoever. It is a 0D model. It is just essentially a chemistry accounting model. But we can imagine how we treat the grain surface is kind of just like a golf ball. We assign the dust grain to have a certain amount of binding sites, in this case roughly 1 million for a typical grain size of 0.1 micron. And as a species accretes onto the surface, it sticks into a dimple of the golf ball. And then it has two barriers to either diffuse around the surface through the dimples, or a barrier to just pop off the grain and desorb back into the gas phase. And then as things accrete, you essentially just layer things on top of each other, and the ice mantle grows. And I just have a list of included reactions if people like chemistry. But it's essentially just out of those 12,000 reactions, you're going to have some cosmic ray interesting reactions, some photoionization, ions, neutrals, et cetera, et cetera. So all of that's kind of the background. The thing that I'm adding to the field, or attempting to, maybe modifying some other work, is to add this grain size distribution. So almost all prior models, with the exception of one, has assumed a canonical grain size. It's just kind of a necessary thing, especially earlier with numerical models in the 70s, 80s, 90s. You can't do too much, and so an easy simplification was assume all grains are the same size and that they don't grow. So you just leave it at 0.1 micron. But of course, in reality, that's not true, and we want to investigate what might change if we were to invoke this distribution. So how do we find it? Well, we just use our extinction curve. We find this background field star. We find a model spectra for a star like that, for a star of similar character, and then we find how it's extincted by this cloud. And most of this extinction is just occurring due to dust. And an individual dust grain of a given size will absorb light of given wavelengths in a certain pattern. There's plenty of theory for this, me theory, or just if your grain is small or large enough, you get into Rayleigh limit, or just blackbody limits. Someone did this in 1977, and I just used his model because it's the most straightforward. It's the easiest way to just throw it in my chemical model and see what happens. And his model just uses a power law for the distribution of how many grains you expect for a given size. Here, A is the radius, so the number of grains per given radius goes as the radius to the minus 3.5. This is, I guess what this tells you is that if you were to plot the total amount of cross-sectional area for a given size of grain, that the total amount of cross-sectional area goes up as you go to smaller grains. And this is going to be important because the grain surface is where a lot of the interesting chemistry occurs. And for chemistry to occur on the grain surface, gas species need to accrete onto that grain surface. And if the small grains have the largest cross-sectional area, they're going to be accreting the most gas, and therefore will be affecting the chemistry the strongest. Okay, so the goal now is to find the effect of this distribution. So how do you, at least initially, might expect this grain distribution to affect the model? Well, one, you might expect as the grains grow and have different sizes, you might expect that the total number of binding sites on the surface might play a role. So the first model here is just a single grain size, the control model. And the next model that I ran is just 5 grains, but with uniform temperature. And so this is just to find the effect of how the different grain sizes might change the chemistry. The next way you might expect the grains to matter, the different grain sizes to matter, is that if you have a different grain size, you might absorb or emit energy in different manners, and therefore might have different temperatures. And a kind of a canonical estimate on how these different grains might have different temperatures is just another simple power law. Astronomers love power laws. And this power law is that the temperature of a grain might go as should go as the radius of the grain to the minus 1/6. So the smaller grain should be warmer. So this is a 5-grain plot distribution with a distribution in both size and temperature. I'll explain how these plots work real quick. And then this last one is just a collapse model. So it's not a quiescent cloud, but collapse models generally try and represent actual physical conditions a bit more precisely. So what I'm showing here is just the radius on the left, and the radius is the dashed lines, and the right is the temperature with the solid lines, and so just how these evolve through my model, time on the x-axis. So we essentially do a model for 10 million years, and you can see that the grains grow in all models. The dashed lines do increase. The sizes here, this is a micron. So for a single grain size, the mean grain size is roughly a micron, whereas here you can see that, oh, sorry, this is in centimeters. So that's smaller than a micron. It raises to about 0.1 micron. But here you can see these grains are growing, but I've fixed the temperature. This is just to kind of disentangle the number of grain binding sites versus the temperature effects. And here you can see that the temperatures evolve through my static model. They actually decrease, and that's because as these ice mantles grow, these grains are essentially, their effective area is increasing, and because the temperature is determined by the size of the grain, as the grains are growing, their temperature is lowering. And so you can see that for the smallest grains that start at roughly 15.5 Kelvin, they end below 13. So now we'll get into the actual chemistry. This is just a representative plot of the single grain control model. This is water at the top. Water is always the most dominant ice species, so I know that that's doing a decent job. Here, the magenta is methanol with blue as formaldehyde, and methanol is a product of formaldehyde, and so they should trail each other fairly well, which they do. Red is carbon monoxide, and green is carbon dioxide, and the 2 dash species are just hydrogenated species, which we don't like to care about because they're not interesting. They don't do much other than just abstract hydrogen. So here you can see that for a single grain, I have mostly carbon monoxide of the 2 carbon and oxygen species. Now getting into the next model, which is where it gets complicated to try and show this, I essentially have an aggregate mantle. This is for the 5 grains with the uniform temperature. This is the aggregate ice mantle. Add up all the ice mantles off the 5 different grain sizes. This is the mantle for the smallest grain, the median grain, and the 5th grain. And you can see if I flip back and forth here, just the general shapes of these plots look roughly the same. And I can show that at the end that the total chemistry doesn't change appreciably between those 2 models. So the grain distribution doesn't really do much if I don't have a temperature distribution. But now if I go from these plots to a distribution in temperature, as you may expect, just even naively, that a temperature distribution probably is going to affect the chemistry because the temperature is what determines how my rates or how my reactions move, right? If a rate constant, well, generally, chemical rates depend on the temperature. And here, the big chemical rate that's important here is the conversion of CO to CO2 through various rates is the most temperature sensitive in the region of 10 Kelvin. So for a temperature distribution that I showed earlier, where the grains have a temperature between 9 and 15 Kelvin, there's a transitionary temperature around 12 Kelvin where CO becomes efficiently converted into CO2. And so here for my smallest grain in a distribution temperature, you can see that the CO2 is actually competing with water for an immense amount of ice formation, whereas CO has dropped off the radar until the grain gets sufficiently large to cool off that CO becomes competitive in the reaction rates again. And even in the aggregate ice mantle, CO2 is dominant because the smallest grain is accreting the most ice. Here's the collapse. I'm just going to skip it because I'm running low. So this is just the table that shows that the single grain model is very comparable to the 5-grain model with uniform temperature. You can just compare all the numbers. They're all about the same. The difference here comes with the temperature difference. There's less water ice because the warmer grains essentially allow water to more easily desorb off the surface. And also the amount of CO has dropped, the amount of CO2 has grown. The amount of methanol has also dropped, and that's kind of a curious thing because you might expect that methanol would grow just because warmer temperatures maybe makes more complex species more easily formable, but methanol generally requires hydrogenation of CO, and if CO is being formed into CO2, the formation of methanol is inhibited. So just a quick conclusion slide. I guess I've probably talked about most of this, so you can just read them. I'm out of time. Thanks.
We have time for one quick question.
Do you allow for bulk diffusion in your grain model? And if so, what's your bulk diffusion
Yes.
rate?
Yeah, so as the ice species get sequestered into the mantle, a lot of previous models would just say the ice is now completely dormant and nothing occurs, and they just build up, and then you can look at the ice at the end. This model does include bulk diffusion, and so you can allow these ice species, even while in the mantle and no longer on the surface, to react with other ice species. It ends up not playing a huge role in this model, but if the temperature were, say, doubled to around 20 Kelvin, maybe in a warm-up stage of a protostar, that can become very important. But for this specific project, it didn't end up playing a huge role.
All right, let's thank speaker again.